Now there is question that transmutation reaction is there. Can we carry out artificially? Let us check out. Say uranium is there, atomic number 92, mass number 238. This is naturally occurring uranium. Now this is bombarded with slow moving neutron. Slow moving means don't consider it is very slow moving, but it is not accelerated one. That means velocity is not given. Whatever natural velocity is there, that. So that slow moving neutron is bombarded on uranium 238. Now neutron is represented as this way, 0, because there are no protons. So 0 and 1. Now on bombardment of this neutron over uranium, we are getting uranium atomic number 92, say 92 plus 0, so here it will be 92, whereas mass number 238 plus 1, so 239. That's why in previous lecture we discussed this is synthetically prepared isotope. Say 92 uranium is already there, but we converted into new isotope of it, that is uranium 239. Now this is, you are aware, beta emitter, and as it emits beta, we are getting new element, that is 93 number. We named this as Neptunium on behalf of Neptune. Mass number remains constant, and that will give again beta emission to give plutonium. Mass number is 239 only, but atomic number 94. So this is series. We are saying these elements here, they are naturally existing, but then onwards they are synthetically prepared or transuranides or transuranic elements. So this way may be possible, we can say, to some extent the transmutation is carried out synthetically. Why? Because atomic number remains same, but after that the radioactivity is there. So on radioactivity we are getting transuranide, but initial source is somewhat artificial. But is it possible that we are getting direct? Answer is yes. Various nuclear reaction. Now what this is called as nuclear reaction only. Here I have shown the reaction, that is nuclear reaction. In order to get this type of nuclear reactions, we required certain thing. Say in case of chemical reaction we are mixing out reagent, but here mixing is not required. Here directly attack on nucleus is required. Now what is the problem over there? That nucleus is possessing out positive charge, and in order to change structure of nucleus, there must be something which is bombarded on nucleus, that is called as projectile. Let us check out again how nuclear reaction is carried out. There is target. Target means the reaction we have to carry out on that particular substance. Say for example here uranium is target. On uranium we are bombarding out neutron. So neutron is bombarded here. This is called as projectile. Don't misunderstand that okay proton. No, this is called as projectile. The particle which is bombarded is called as projectile. On bombardment we are getting new nucleus here. We are calling this as recoil nucleus, and sometime it is followed by emission, or that is called as ejectile. So nuclear reaction, I can say this way, that target is bombarded with projectile. In return we are getting recoil nucleus and ejectile or emission. Not necessary. Now in this case there is no ejectile directly, but it may there. Now here we are getting different ideas. Suppose I had to bombard projectile, then projectiles are proton, deuteron, alpha particles. All are possessing positive charge, whereas nucleus of an atom, say this is atom, this is nucleus, this is also having positive charge around it. The moment particle which is already positively charged, which is approaching to this, it is having first electronic cloud, but electrons are having less mass. So with high velocity this particle can pass out through electronic cloud, But here also strong positive charge is there. The moment it will approach, it will repel back with greater speed. Why? Because nucleus is having strong positive charge. In case of uranium, you are aware 92 protons are there. Whereas, suppose I am bombarding with alpha particles are having plus 2 charge. So plus 2, whereas 92 plus 2. So here plus 92 and plus 2 will repel back. This is called as Coulombic barrier. That means repulsive force between nucleus and projectile. Now in order to overcome this force, there must be tremendous energy required. Now obviously this particle is having positive charge. I have to accelerate it. I have to increase the velocity. On increasing velocity, these particles get bombarded on nucleus. But this is very easy for me to say that okay, we have to accelerate particle, but it is bit difficult. Why? Because for that purpose certain instruments are required. They are called as particle accelerator. For example, the first particle accelerator was built up that was having length of 9 kilometers. Imagine 9 kilometer length is there for instrument that is called as linear particle accelerator. Then there are other particle accelerator device developed. They are called as cyclotron, which was having considerable less length. Then it was developed syncyclotron, more effective. But still these particle accelerators are required in order to bombard projectile over target. And that's why we are considering here neutron as a best projectile. Why? Because neutron is not possessing charge. So it can pass out through this electronic cloud and hit the target, that is nucleus, very easily because it is not having any charge. And so not accelerated neutron also work. So we are using word as slow moving neutron. So this way reaction we can carry it out in consideration. These reactions are called as nuclear reactions. By use of the nuclear reaction, various new isotopes were produced. Like here we produce uranium-239, which is not naturally existing. Same way we produce various isotopes of various elements, and even radioactive element of early element. Early means less than atomic number 82, that is lighter element, that is also possible. So for example, carbon we can make radioactive, we can make oxygen radioactive, we can make phosphorus radioactive. Like that, various elements which are non-radioactive, we able to make them radioactive by using various particle accelerators, various projectiles. We are able to produce out new particles, new charge bodies, and that's why we are calling that as nuclear reaction. In the nuclear reaction, suppose lighter elements are produced which are possessing radioactivity. We are calling that as artificial radioactivity, or even we may call it as induced radioactivity. This way we got various nuclear reactions. Now we are switching over to another topic, that is how radioactivity is measured. In order to measure radioactivity, we are using simple instrument. This is called a scintillation counter. The device initially was set up something like that. This is say brass tube. Why brass tube only? Because various old instruments were made up of brass. Brass is comparatively dense alloy, and that is used because we want complete darkness inside the tube. Now here we are placing out zinc sulfide screen. So this is zinc sulfide screen. Here there is position to mount radioactive substance. So here radioactive substance is mounted over here. Then here we are simply closing out it off. Here there is single hole, and from that suppose I have to observe. So this is the human eye observer. Now we are placing out radioactive substance over here. There is complete darkness inside the tube. There is only one aperture where from that one can observe what is inside the tube. That fellow must have stopwatch in one hand and counter in another hand. Simply we have to on stopwatch and start observing inside the tube. You will get scintillation. Scintillation means this zinc sulfide screen will glow in white color. Count out 1. Now your stopwatch is on continuously. The moment you observe scintillation, count out. The moment you observe scintillation, count out. Like that, we have to observe for 15 minutes or whatever the longer period you can observe. So that way we can able to observe here for 10 minutes, 15 minutes, 20 minutes, whatever that. And then stop the stopwatch, check out the count. How many times this screen blink out or we are getting scintillation here. This is simple scintillation counter. Now we are having now mechanization. Instruments are developed in order to observe that. Instead of that, we can check out here with various sensors and we can get accurate result. Number of scintillations. Now how radioactivity is measured? Number of scintillations per gram of substance. So I have to place here 1 gram of substance, then observe, and per minute. So how we can check out number of scintillation per minute per gram of substance. So this is called as radioactivity, or simply we can say number of scintillation per minute. Okay. So like that radioactivity are we can measure out. Now we are aware that there is unit that is Curie, that is named as Curie. That means 1 scintillation per minute. That is called as 1 Curie. Per gram is now understood that because as number of atoms increases, scintillations also increases. Now the way we are measuring out radioactivity, again question is that what exactly it works, how it works. Now we are having little bit knowledge now about radioactivity, and from that we are going to somewhat deeper knowledge. Number 1, we have to consider here that suppose there is element as we discussed in earlier way, that uranium is there, atomic number 92, mass number 238. As we say, this is try to recollect, this is alpha emitter. So as it emits alpha particle and converted into thorium, atomic number 90, mass number 234. It is not necessary that all uranium atoms should emit alpha particle at a time and get converted to thorium. No. Keep in mind, uranium, all atoms will not emit alpha particle at a time. Only few of them will emit. Rest of will remain as uranium only. The few will emit alpha particle and then they are converted to thorium. Now, if you check out graphically, on x-axis we are taking amount of substance, and on y-axis, and on x-axis we are taking time. The graph showing is expected graph is something like this, decreasing. That means amount of uranium, suppose I am showing uranium in green color, the amount of uranium will decreasing out, whereas amount of thorium, now here thorium is there, so initially it will be 0, but it will be increasing out this way. So this is amount of thorium. So some sort of this type of graph is produced. Let us check out first what exactly happened over here. The moment uranium decreases, say there are 100 atoms of uranium initially, 2 will give thorium. So initially 0 thorium, but now there are 2 thorium atoms. Then 2 will disintegrate. Disintegrate means emitting out radiation and converting into new element. So 2 will disintegrate, or it is also even called as decay. Then we are getting 2 more atoms of thorium. So like that, this way the amount of this substance is decreasing out, amount of this substance will increase. Now, practically determined data shows it will take infinite year for element to disintegrate to 100%. Then we can check out another concept. We are calling that as half-life period. That is time taken by element to reduce half of its activity, half of its initial activity. That is called as half-life period. Now uranium, suppose initially I have 100 atoms and uranium is having half-life period of suppose 1 hour. So after 1 hour I am getting half atoms converted into thorium, whereas half will remain. Again after 1 hour, say I am constructing this graph again now. So here on x-axis we are taking amount of substance and on y-axis we are taking time. So suppose we are saying it is not, but we are saying 1 hour, 2 hours, 3, 4 and so on. Here there are suppose 100 gram. I am saying not atom but 100 gram. So here T equal to 0 because at beginning we are observing. So this is the first point, 100 gram. Now half-life period is suppose 1 hour. So after half-life, that means after 1 hour, what is initial activity? 100. Of that 50% will remain. So this is the amount of substance remaining, whereas this is the amount of substance converted into new element, that is thorium. Now after 1 hour, whatever the initial amount, not this now, of this half will be converted. Getting idea? So here initial amount is this. After 1 hour it will be half of it, and so we are getting graph like this. After 1 hour, now this is the period, half of initial amount will converted into thorium. So this is half of that. So I have to point here. Again after 1 hour, half of it. So again half of it. If you put out value here, it is 100, it is 50, it is 25, it is 12.5, it is 6.25 and so on. So this way amount of substance decreases, and that's why we have shown this graph like this. Now check out the slope of graph decreases. Now here at first incident we can check the 50% is converted into thorium. So assume the amount of thorium is also 50%. Then onwards 25, that means here I have to go total 75 grams are available with me, suppose. Then still more, so 75 plus 12.5, that is 87.5. Then I add 6.25. So like that we are getting more and more thorium. So my graph of thorium is going like this. So this is the way radioactivity is taking place. But this graph is number of atoms converted into thorium. But thorium also radioactive because its atomic number is 90. And so thorium will not remain as it is. It will start disintegrating again. And so in this case I am calling this as parent element, whereas this element as daughter element, not son element. this is daughter element. Again thorium will have same type of graph, and like that continues till we are getting stable product, that is uranium, that is lead atomic number 82. So this way radioactivity works. Here the important concept we discuss, that is called as half-life period. Now with this graph we can calculate amount of substance remaining at any time. Say my initial amount, I am showing here, initial amount is, I have to consider N0, that is N at time equal to 0. The final amount I have to say NT, that is number of atom at time equal to T. So here I should say N0 is 100, whereas NT, suppose I am saying here, then NT will be 50, like that. Suppose I have to check out what will be the amount in half hour. Can I check out? Answer is yes. On this graph I have to draw line, and then I can give this is the amount after half an hour. But by using some formula also we can do that. So you are aware now, N0 is initial amount, NT is final amount. Then there is a constant, we are calling this as lambda, that is decay constant, disintegration constant, or radioactivity constant. Then there is concept T, as on this graph I have to check after certain time. So formula is that T equal to 2.303 upon lambda. Now there is introduction of term log of base 10. Base 10 means whatever normal log we are calculating, that is base 10 only, N0 upon MT. So if we have time knowledge, we have value of lambda, we have N0, we can calculate NT. But for that purpose certain things are required. So first thing I have to go by half-life period. How to get lambda? For that purpose, say first thing you have to by heart this formula. This formula is very essential. We can say this is first order reaction, and in chemical kinetics also similar formula is applicable. Now here I have to explain half-life period on basis of this graphical, not graphical, equational way. So half-life period, what definition is there? Time taken by element to reduce half of its initial activity. That means here my N0 is 100, NT will be half of it, so NT must be 50. Then that time is called as half-life period. So I am substituting all these in this value, so it will be T half equal to 2.303 upon lambda into log base 10 of N0. N0 is 100 upon NT is 50. So check out for any value, you will get log of 2 only. So suppose I am saying N0 is 1000, NT will be 500. Again we are getting same log of 2, and so we are getting formula, that is T half equal to 2.303 into, now log 2 is having value 0.3010, check out from log table, upon lambda. So here I can say lambda equal to, this multiplication comes as 0.693 upon T half. So this is the formula we can use to calculate value of lambda. That's why we required here half-life period. Without knowledge of half-life period, we are not able to calculate that. Once you are aware of half-life period, you are having value of lambda. Substitute lambda here. N0 we are aware, that is initial activity, initial amount, whatever that. Then if T is known, we can calculate NT, and if NT is known, we can calculate T by substituting in this formula. So kindly write down this. We are not going into discussion derivation of the formula, but I have explained here utility.